Welcome students, this is the second part of our series Real Numbers of class 10 Telangana syllabus as well as AP syllabus. So today we are going to discuss about the second problem of this exercise 1.1. So here we can see the second problem. Use Euclid's division lemma to show that any positive integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5, where q is some integer. Now let us see how to solve this problem. First of all, we will take let a be an odd positive integer, an odd positive integer. So now we will apply division algorithm on A, and we know that here B is equal to 6. So we will apply Euclid's division algorithm on A. By applying Euclid's division algorithm on A. So A is our positive odd integer. So now we are applying the Euclid's division algorithm. So here we can say that since we have the formula 0 less than or equal to remainder less than 6. So if this is the condition, so the remainders will be starting from 0, 1, 2, 3, 4, 5. So these are our remainders. Now we will substitute these values in the equation. A is equal to bq plus r. So here, so the b will be 6q plus 0. That is nothing but 6q. So this is our first value. Similarly, the second one will be A is equal to bq plus r. So here 6q plus 1. So this is our second one. A is equal to bq plus r. So 6q plus 2. Why? Because the remainder they are starting from 0, 1, 2, 3, 4, 5. So next we will get A is equal to 6q plus 3. Similarly, we will be getting A is equal to 6q plus 4. A is equal to 6q plus 5. So these are our values of A. But in the problem We know that A is an odd number, but we know that A is an odd number. So here, if the number is odd, now we can't take this one PQ 6Q plus 2, 6Q plus 4, but we can take 6Q plus 1, 6Q plus 3, 6Q plus 5. So these are our odd numbers. So as the question is asking us to find out the odd numbers, so we can finally say that therefore any odd integer is of the form 6Q plus 1, 6Q plus 3 or 6Q plus 5. So hence we are able to show that there exists a positive odd integer which is nothing but 6Q plus 1, 6Q plus 3, 6Q plus 5. So this is our solution to this problem. Now let us see the next problem, third one. Use Euclid's division algorithm or lemma to show that the square of any positive integer is of the form 3p plus 1 and 3p plus 2. So for that we will take the value. Let a be the square of an integer. So we'll write like this. Let a be the square of an integer. So now when we are applying Euclid's division lemma on A, here you have to remember B is equal to 3. So we can satisfy this condition since 0 is less than or equal to r less than 3. So this is our condition. So when you are satisfying this condition, so the remainders will be starting from 0, 1 and 2. Here you have to remember one thing, as the value of b is 3, so we'll have the remainders from 0, 1 and 2. That is one number less than 3. So again now by using this a is equal to bq plus r. So here what is our b value? 3. Q. Our remainder will be, we'll take 0 here, plus 0 which is nothing but 3p. So similarly for the second one, a is equal to bq plus r. So 3q plus 1. Okay. So now we will take the values of in the quotient p is there. So we'll take it here p. Instead of q, I'll take it as p. I'll be changing this q as p so that we will not have any confusion. So here it will be 3p, that is nothing but 3p, but here it will be q in the formula. So 3p plus 1. So similarly, a is equal to bq plus r. So we can write 3p plus 2. So similarly, we get a is equal to 3p. So here we are getting the three values, that is, one is 3p, the other one is 3p plus 1, the next one is 3p plus 2. But here he is telling that the number is a square of any positive integer. So for that we will see, let a be a positive even integer. So a is our positive even integer. Then a is of the form 2p. So we can say that a is of the form 2p. Why? Because it is even. So now what we'll do, we'll square on both sides. A square is equal to 2p square. So now we'll get the value of 4p square, which is nothing but, I'm taking 2 common, so 2p square full bracket, or I'll take this 2, in place of 2p square I'll write k. Why? Because here I'm taking the value of k as 2p square. So here this is the case for even integer. So if the value of a is odd integer, suppose you will see that a is a odd integer, so then here we'll take the value of a is equal to 2p plus 1 whole square, that is squaring on both sides. So I will be getting, so this is in the form of a plus b whole square. So that is nothing but a square plus 2ab plus b square. So I will be getting the form of 4p square plus 4p plus 1. So if I take out the common 2 here, so it will be 2p square plus 2p plus 1. So I will write this as k plus 1. So this is an odd integer. But according to the problem, here it is 3p. Okay, so we'll see here a is equal to 3p, a is equal to 3p 1, a is equal to 3p plus 2. So if we are considering these values, then we can say that, so p is our quotient here. So p is our quotient, and the remainders are 0, 1 and 2. So here finally we can say that any square number is of the form 3p plus 1. Similarly 3p plus 2. So this is our solution to the third problem of this exercise. Now let us see the next problem, fourth problem. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. You have to show that cube of any positive integer. So for that, as usual, you have to take the value of a. Let a be the cube of a positive integer. So here, now applying Euclid's division lemma. So what I am getting here, as you know, b is 9 here. The value of b is 9. So obviously, I will be having the reminders as 0, 1, 2, 3, 4, 5, 6, 7 and 8. So these are my reminders. So therefore, we can write a is equal to bq plus r. So now in place of q, I am writing bm plus r. So this b is nothing but 9m plus 0, that is nothing but 9m. So similarly, I will be writing a is equal to bm plus r. So 9m plus 1. So similarly, I can get the values of a is equal to 9m plus 2, a is equal to 9m plus 3, a is equal to 9m plus 4, 9m plus 5, 9m plus 6, 9m plus 7 and 9m plus 8. So these are all the values which I am getting. So which are nothing but cube of any positive integer. Now let us see the next problem, fifth one, and the last problem of this exercise. Show that one and only one out of n, n plus 1, n plus 2 or n plus 4 is divisible by 3. So here we have to remember that there are 4 values n, n plus 1, n plus 2 and n plus 4, which we have to show that they are divisible by 3. That is, only one value is divisible by 3. So for that, let us take let a is equal to n or n plus 2 or n plus 4. But we know that b is equal to 3 here. Okay. Now by Euclid's division lemma, so we are taking a is equal to bq plus r. So here, as the reminders will be 0, 1 and 2. So here our reminders will be 0, 1 and 2. So I will be getting the value of a can be n, n plus 1 or n plus 2. according to the division lemma. N divides, it divides n plus 4. So it leaves a remainder. It leaves a remainder as well as this n plus 2, it also leaves a remainder. So both these numbers, that is n plus 4 and n plus 2, they will be giving a same remainder as it divides. So finally we can say that only one out of n plus 2 or n plus 4 is divisible by 3. So this is our answer. So by this we conclude to the end of exercise 1.1. So students, if you are able to understand these problems, please do like, share and comment, and do subscribe to my channel to get more and more videos like this on maths subject, especially for 10th class. Thank you very much for watching this video.